Okay, so we were on question 4. We had 1.2 meters. We were going to multiply it by our 1.602 to the negative 19 coulombs, and we were going to multiply it by our 0.36 Teslas, and then that gets divided by the 1.673 to the negative 27 kilograms. And when you type all that into your calculator, you end up getting a speed of 6.8944 times 10 to the 6 meters per second. Okay, number 4. Number 5, electrons move in a 4 MT, so millitesla magnetic field. Tells us the R is 2 centimeters, and it wants to know what is the speed. So exactly the same question again. Again, you're going to take your R equals mv over qb and rearrange for v. So v is going to equal r qb over m. So v is going to equal 0.02 meters, 1.602 times 10 to the negative 19 coulombs, and the magnetic field is 4 times 10 to the negative 3 Teslas, and then you're going to divide by 1.909 this time because it's an electron, to the negative 31 kilograms. And then you're going to punch all that into your calculator. So 0.02, 1.602 to the negative 19, and 4 to the negative 3, and then divided by 9.109 to the negative 31. And I believe you get 1.4, you get a speed of 1.407 times 10 to the 7th meters per second. Oops, be good if I was actually on the screen with it. Okay, and then the second part, what would the electric field need to be to make it go straight? So now we just go back to E equals VB. So we take that 1.407 to the 7th meters per second, and we're going to multiply it by the 4 to the negative 3 Teslas. And so you are going to get 5.627 or 5.628, 5.6278 times 10 to the 4th, and that'll be newtons per coulomb. Okay, so number 5, that was. Number 6 says, what energy must be given to an electron to transfer it across a potential difference of 4 to the 5th volts? Okay, so for this one, it goes back to our equation V equals EK over Q. And so it's looking for energy, or EK, it's just equal to Q times V. It does say an electron, so 1.602 to the negative 19 coulombs, and you are going to multiply that by 4 times 10 to the 5th volts. So EK is going to equal, what is that, 6.408, and that's 5, so times 10 to the negative 14 joules. And if I screwed that up, it's because I didn't use a calculator, but I think it's right. All right, number 7. A proton enters a 6 times 10 to the negative 2 Tesla magnetic field, speed of 5.4 to the 4th meters per second. What is the radius? So again, we're just going to use R is equal to mv over qb. This time we don't even have to rearrange it. It says it's a proton, I believe. Yeah, so 1.673 to the negative 27 kilograms. Its speed is 5.4 to the 4th meters per second. Q 1.602 to the negative 19 coulombs. And B 6 to the negative 2 Teslas. punch it in your calculator. 1.673, 27, 5.4 to the fourth, divide by 1.602, negative 19, and 6 to the negative 2. And you should get 9.3988. 9.39888 times 10 to the negative 3 meters. Okay, and the last one that I asked you to do for today's class, proton enters a magnetic field. What is the circumference? So again, you're going to solve for R. R equals mv over qb. So again, it's a proton, I think. Yeah. So 1.673 to the negative 27 kilograms. Its speed was 4.5 to the fourth meters per second. Q 1.602 to the negative 19 coulombs, and the field 6.4 to the negative 2 teslas. Okay, so 1.673 negative 27, 4.5 to the fourth divided by 1.602 to the negative 19 divided by 6.4 to the negative 2. So you get a radius, if I type that in correctly, of 7.34287 to the negative 3 meters. But that's not what the question asked. Question wanted circumference, which I'm hoping you know is 2 pi r, not r squared. So take the number you have, multiply it by 2, multiply it by pi, and you should get 4.6. I was just confirming that that's right. 4.61366 times 10 to the negative 2 meters. Okay, so that was it for your homework questions from yesterday. If we're not in school tomorrow, or even if we are, if you want to keep going, you could do numbers 10 to 14. The other thing I would have done in today's class, if we had not had the assembly, was I would have talked about generators, and it's the second part of your notes. So the sheet of notes I gave you yesterday was on electric generators invented by Michael Faraday, and we've talked about Faraday already. And all it does is it converts electrical energy into mechanical energy into electrical energy. Okay, so really what it is you have a magnet, okay, north and a south. You have a coil of wire. So you just coil of wire that's in between the poles. And what we're going to do is that we're going to turn the coil. So this side's going to go up and then go back down over here. So it's going to go like this, okay? So it's going to start on this side. And so if you imagine, as it comes up, this edge right here is going to leave the field. And as it leaves the field's going to be getting weaker. Weaker field is changing field's going to cause an induced current. And so the current's going to flow in this side of the wire in a particular way. As it comes up, the field's getting less, and as it gets less, so remember, EMF is equal to B, excuse me, that's not a B, BLV. So as the field gets less, the current that's going to be induced, the voltage that's going to be induced, that's then going to create a current, will be tiny. And so that's where we had said it's sinusoidal. And so the current that's induced is going to change as you come up out of the field and then go back down. Now, if we were to do hand rule, take your left hand, run it north to south. The wire is pointing upward, or moving upward, which means the current when it's on this side would be going this way. But now when it comes over here, now it's going down. And so when this